the Solar Nebula. This initial stage marks the very beginning of our world, emerging roughly 4.6 billion years ago as a massive rotating cloud of interstellar gas and dust. It originated from the collapse of a giant molecular cloud, likely triggered by the shockwave of a nearby supernova explosion. What made this phase distinct was that Earth did not yet exist as a distinct body. Instead, its future raw materials were scattered as microscopic grains of silicate rock, iron, and ice spinning within a flat, chaotic accretion disk surrounding the newly forming proto-sun. It matters fundamentally because this rotating cosmic debris field set the chemical composition and the orbital direction for everything that would eventually build our modern planetary system. Planetesimals. These solid objects represent the first physical building blocks of our world, forming over millions of years as microscopic dust grains within the solar nebula collided and stuck together through electrostatic forces and gravity. They originated in a highly crowded and violent inner solar system, growing from tiny pebbles into rocky metallic boulders, measuring several miles across. What made this phase unique was the transition from passive chemical accumulation to active gravitational attraction, as these larger bodies began aggressively sweeping up everything in their orbital paths. This era is a crucial chapter in geological history because the chaotic clustering and constant fragmentation of these rocky bodies provided the immense physical mass required to eventually build a full-scale planet. Proto-Earth. This growing planetary embryo emerged as a dominant force in the inner solar system, reaching roughly half of modern Earth's size after absorbing thousands of surrounding planetesimals over a period of 10 to 20 million years. It developed with a primitive, highly unstable structure that was constantly bombarded by remaining space debris, keeping its surface in a volatile, semi-molten state. What set it apart from its earlier forms was the initiation of planetary differentiation, a process where intense heat from radioactive decay and constant impacts caused heavy metals like iron and nickel to sink toward the center, forming a dense metallic core, while lighter silicate rocks floated upward to create a primitive mantle. This phase matters profoundly because it established the structural foundation and magnetic potential necessary for the planet to eventually support an atmosphere and a stable surface. The Magma Ocean. This terrifying phase transformed the entire planet into a glowing, liquid ball of fire, following a cataclysmic collision with a Mars-sized planet named Theia. This monumental impact, which occurred roughly 4.5 billion years ago, released so much kinetic energy that it completely melted the outer layers of the planet and blasted a massive ring of vaporized debris into orbit that would eventually condense to form our moon. The defining feature of this era was a global ocean of molten rock hundreds of miles deep, topped by a thick, suffocating atmosphere of vaporized silica and greenhouse gases. This extreme melting event was highly significant because it thoroughly mixed the planet's chemical components, finalized the size of its core, and set the stage for the first solid crust to crystallize as the planet slowly radiated its intense heat out into the freezing void of space.